What's the hurry? When solid-state batteries come out, I'll just buy one then. What exactly makes these batteries solid? Is it like ice? Or like an ice pop? Where exactly is the solid part? Let me explain. The biggest difference, perhaps the most significant difference, lies in the electrolyte. A regular lithium battery mainly consists of cathode material, anode material, liquid electrolyte with separator, and current collectors. During discharge, lithium ions deintercalate from the anode, travel through the liquid electrolyte, pass through the separator, and return to the cathode material. Solid-state batteries essentially combine the electrolyte and separator into a single solid material. Imagine it like this. Originally you had a pool of water, where ions could swim from left to right. Now, somehow this pool has turned into a solid rock, yet the ions can still move from left to right through it. Current research mainly focuses on two directions: inorganic solid electrolytes and polymer electrolytes. Inorganic solid electrolytes are generally oxides or sulfides, while polymer electrolytes are essentially organic macromolecular materials. Different domestic battery manufacturers are pursuing different electrolyte research directions. Remember how everyone's been debating whether lithium iron phosphate or ternary lithium is better. In a couple years, the debate might shift to whether oxide or polymer electrolytes are superior. That's the general feeling anyway. We're not researchers after all. So why are researchers going through all this trouble to change the electrolyte to solid materials? First, there's a clear advantage: the batteries become more heat resistant and safer. Look at this chart. The bottom two with thermal runaway temperatures below 200 degrees C are regular lithium batteries. When you switch to solid materials, even the decent ones can withstand 400-500 degrees C, with some not experiencing thermal runaway until over 1000 degrees C. This makes the batteries significantly safer, and the improved heat resistance also means they can handle higher charging power. Take Toyota's claims from a few years ago. They said their solid-state battery could charge in 10 minutes for a 1,200 km range. Compared to current top performers that need 15 minutes for 600 km, that's indeed faster. Here's an interesting data point I found. A July 2024 article mentioned Toyota holds over 1,200 patents related to solid-state battery electrolytes, accounting for 15% of their total. Isn't that different from what you might expect? They haven't made much noise about actual vehicles, but they're cranking out patents like crazy. Are they trying to recreate their hybrid vehicle success story? Another benefit of replacing liquid electrolyte with solid material is that the separator becomes unnecessary, which extends battery life. Originally, the separator was there to prevent electrons from moving haphazardly between electrodes and causing short circuits. But during discharge cycles, as ions pass through the separator, they gradually form crystalline deposits. Over time, these crystals can pierce through the separator and cause short circuits. It's somewhat like how uric crystals accumulate and eventually cause gout pain in your joints. With solid electrolytes, this problem disappears. No need to worry when your leg is made of stainless steel. Finally, there's another advantage: the anode material can use lithium metal, which increases energy density.